Good morning, good afternoon, good evening, wherever you are on the planet. My name is Torsten Hoefler. I'm a professor at ETH Zurich, and together with Maciej Besta, I have the honor to present this tutorial at the very first Learning on Graphs conference, a quickly emerging field today. So the tutorial is going to focus on parallel and distributed graph neural networks. That is the foundation of much of what this conference is about. Learning on graphs is very much a deep learning on graphs with graph neural networks. And we're going to present an in-depth concurrency analysis, really all the performance aspects and the aspects you may need to implement systems from the small scale to the extremely large scale supercomputer-sized systems for the processing of graph neural networks. Our tutorial bases on the paper that you can see in the background with the same name. That paper is on archive. It has about 27 pages, and you can refer to the paper for greatest details that we may not be able to cover in this relatively short 90-minute tutorial here. But again, we try to give you the overview here, the essence of the paper, and then if you want to really dive in all the equations in the detailed systems aspects, please refer to the text, and it will also be on most of the pages at the bottom. So now, to just introduce in general, as we all know, we wouldn't probably be here, that graphs are extremely powerful and ubiquitous. Just to motivate you, social science, we all know social networking bases on social graphs. Engineering, much of it bases on large-scale graphs. Biology, brain-scale graphs, extremely large-scale. Chemistry, looking at bondings, looking at new materials. Communication, our communication networks can be modeled as graphs. Medicine, much of the effects of medications on the human body can be modeled as graphs. Furthermore, cybersecurity, web graph analysis, and even philosophy are basing on very large scale, sometimes very large scale graph problems. So actually, these very large scale graphs are of tremendous size. So we have done an experiment or performed a very large-scale calculation on the largest supercomputer on the planet at the time in 2018. So we processed 70 trillion edges on 10 million cores together with our Chinese partners at Tsinghua University. Here, there was a 12 trillion edge real-world internet graph that we could process in 8.5 seconds per iteration. That is quite challenging. This was, in fact, a finalist for the Gordon Bell Award that is yearly given to the highest performing supercomputer application in the high-performance computing field. And this may still be the largest documented single graph run on the largest machine today. So now the question is, how do we go from here to processing these large graphs? Well, as I mentioned, graphs are extremely large. So what are the computational properties? They're extremely irregular. This is much harder than today's computations. They're communication heavy and synchronization heavy if you go parallel. Furthermore, they're extremely power hungry and can be quite time consuming in practical processing. So now we have processing of very large sparse data structures graphs and deep learning, which traditionally has been quite dense. So if we put these two together, we get graph neural networks, essentially. And learning on graphs has been a very trendy, field the last couple of years, as we know. So this is something that we should get into and understand how to do processing. Because, as Geoffrey Hinton mentioned in his 2018, in his part of the 2018 Turing lecture, really the deciding factor of the AI or deep learning revolution was the increase in compute power. Furthermore, he believes that a lot of credit for the deep learning development goes to people that developed the data sets, but also the people who made the computers go fast. So this is now incredibly important. How do we make computers go fast for graph computations, graph neural network computations, graph deep learning? So how do we make these computers go fast? Well, we can ask last year's Turing Award winner, Jack Dongarra, who spent his career on making computers go fast for dense computations, for high-performance computing, extremely large scale. So he and partners achieved that massively parallel systems are now more than 70% efficient at full scale, at the largest machines on the planet, millions of cores running dense linear algebra. And as you know, most of the deep learning is in fact dense linear algebra. Processing models like GPT-3 is a lot of matrix multiplication. However, the same system delivers only 0.1 0.8% efficiency for sparse problems. So to quote Jack, think about having a race car that goes 200 miles per hour and you get only 2 miles per hour out of it. But unfortunately, that's most likely not going to make you very happy. So there's still a lot left at the, plenty of room at the top, as we can see here. And the top is the software environment. How do we use these computer systems most efficiently in order to actually implement graph neural networks in a way that they're cheap and scalable to extremely large scales? So with this in mind, we wrote this paper that I mentioned, that we need to understand parallel processing of graph neural networks. Because GNNs fundamentally combine dense computations like standard deep learning with sparse computations like graph processing. And this is a very challenging point to make, a very challenging problem to solve. Furthermore, there are lots of different options ranging from extremely fine scale parallelism to very coarse scale, cluster level, supercomputer level parallelism. And in this tutorial, we will be covering all of these options. But before, let me give you a little bit of a rough background of deep learning in a nutshell. I'm pretty sure that most of you probably know it. I just want to put us all in the same stage that we can follow the talk equally well. So we have a set of input examples, and we call samples here. We have a network structure, a deep neural network structure, and then we take one of those input examples, like this cute cat here, run it through the deep neural network, which now implements a learnable function, f of x. X is the input sample. And then we learn the model. I mean, this function is essentially the model. Then we have some kind of prediction of the model, and we look at the ground truth. In this case, it's a cat. And then we do a layer-wise weight update iteratively until the model converges to a good prediction, to the cat. There are now different ways to train, to feed these samples to the model. We could first, before we do a weight update, run all of the samples through the model, which is called a full batch method. Unfortunately, it's extremely expensive because typically we have a lot of samples, but we get a pretty good estimation of the gradient here, and we get a pretty good convergence, but extremely slow computation. Of course, this depends on the quality of your data, as you know. Typically, what people do is they take a part of the mini batch, or a part of the batch, which is then called a mini batch, then that uses a less accurate weight update. It's only a statistical sample, so we take random samples, but has much faster computation, and at the end converges much faster in more steps typically, but much faster in compute time to a good solution. So we'll be focusing mostly on mini batch, but we'll see in the remaining talk. Then if you look at parallelism in traditional deep learning, what does that mean? Well, we have the model itself, and the model can typically be expressed as various layers. I mean, you see a very complex set of layers here. Here at the bottom we have a simpler set of layers. We have very simple convolutional input layers, then two layers that now have filters, and then the output layer, which is a simple classification layer in this particular case. So we can define parallelism on the data, or we can define parallelism on the model. The data is usually relatively simple. You cut multiple examples and run them separately through copies of the model. The model is more complex because it has more options to be processed. So now let me talk a little bit more in detail in this parallelism in deep learning, traditional deep learning. So we are still not at graph neural networks. That's going to be more complex. But in traditional deep learning, what we could do with data parallelism, we have basically full copies of the model here, blue, yellow, and green. And these full copies, they get a part of the mini batch, of each mini batch. So we run it in parallel, and then we sum this all together at the end. Here, for model parallelism, which is an orthogonal way to parallelize, so we can combine these ways of parallelism, and actually typically for very large models this is the case, we could cut each of those layers that we are seeing in multiple pieces and process them on different devices. So we could now take the data parallelism and on top of it model parallelism and process each layer on different devices, which is typically very communication heavy. So that's typically the last form of parallelism that you want, but it speeds up your model. If you simply want to get a higher throughput, or you want to get, you want to fit larger models in your limited size accelerators, you could go with pipeline parallelism, where you take each of those layers, the blue, the yellow, and the green layer here, and put them on separate devices. And now you could, of course, imagine that you can combine all of these three forms, data parallelism, model parallelism, and pipeline parallelism, into a single parallel system, a parallel computation system that now works on all these three dimensions. Okay? So this is standard deep learning, or let's say traditional deep learning, which is typically dense computation today. There's, of course, sparse computation in these models as well, but most of the models today are processed, learned densely. But now if you look at graph neural networks, how does this model change? How does this view change? Well, again, we have a very similar picture here. We have the input samples, but now these input samples, they could still be photos, but they are related by explicit relations. So now a photo would not just be a part of a set, but it would actually be a vertex in a graph, and it would be connected to all the other vertices based on some certain on some specific property. For example, if the photos are taken in the same place or at a similar time, they could be connected by edges. Right? So now each of these little pictures is a vertex. Then we typically run each of these pictures also through a deep neural network, but these deep neural networks are very often simpler than the networks we have today. And other tutorials talk about how to increase the complexity, how to grow the complexity from a data science perspective. We are going to talk about it from a computational perspective here. So keep in mind they're typically much smaller on graph neural networks for various reasons that we don't cover here. So now what we do is we take an input sample, which is now not independent, or which may not be independent. You can see here that has connections to other input samples. We gather the information from the neighbors, and that is now a big difference to traditional deep neural networks because there are no neighbors. We apply some graph neural network, or some deep neural network, which is often quite simple, to the information that we gathered from the neighbors. And then we have an optional nonlinearity in our system, and then we move on to the next layer. The next layer quite often means just to rewind to the beginning and repeat the operation over and over again. This is why layer is in quotes. So the definition of layer in our context is twofold. We first have a graph neural network layer where we repeat the operation and get a larger reach, because every single time you collect your neighbors and see more and more and more of the graph. But there's also another definition of layer, like in this little deep neural network, there are of course also multiple layers. So there are lots of degrees of freedom how to construct these graph neural networks. And then once we processed all the layers, we have an output vector which we can then use in a simple classification network, for example, for learning specific tasks. Okay, so basically summarizing this here, we have these different forms of parallelism: data parallelism, model parallelism, and pipeline parallelism. We also have these different forms of parallelism in graph neural networks. But here it's a bit more complicated, because specifically we have different forms of parallelism in the different forms of graph parallelism, data parallelism on the graph. So there could first be graph parallelism, which we could also call partition parallelism. And then this is the left side, where we have one large graph. Remember the 17 trillion vertex graph that we are learning a model on. So this model could either learn specific features of vertices, or it could learn a specific feature of the overall graph. But we also have mini-batch style parallelism, where we would then look at subsets of graphs, where we could have multiple graphs, in fact, and we could look at dependent mini-batch parallelism or independent mini-batch parallelism. So dependent mini-batch parallelism means we have graphs that are relatively large that we need to cut, and where the single vertices still go into different models. But in the independent mini-batch parallelism, what we usually do is we run graphs independently, pretty small graphs independently through the model, which is very similar to traditional deep learning. Now in the model parallelism side, we have a very similar set of options. So we have deep neural network parallelism, where the network that sits on top of each vertex or edge, Maciej will go into that, on that in great detail, will actually be separately processed or can be distributed. We have operator parallelism, which is very much the same as the operator parallelism that we are seeing on the left side, which here on this slide is called model parallelism, but it should really be called operator parallelism. And then we have pipeline parallelism, which is the same as essentially the deep neural network we had before, the traditional deep neural networks, but the pipeline parallelism itself is actually has now two options. There's the pipelining on the graph neural network layers, which is this iteration that I mentioned before, but there's also pipelining within a single deep neural network that sits on top of each of these vertices or edges. So with that, I would like to give the word to Maciej after giving you the motivation and the overview of this tutorial, and he will go into great detail on the computational aspects of all of these graph neural networks, and also the parallelism aspects that I've just summarized here to give you a rough roadmap of the talk, and he will explain all the details. Thank you very much, and hopefully see you in real life at some point.
Okay, wonderful. So yep, thanks Torsten a lot for the very nice first part. Let's now proceed with all the details. So in the second part of the tutorial, we'll first take a very brief recap at some of the important aspects of GNNs that we'll need in the far parts. Then we will take a look at all the foundational aspects of parallelism. So we'll take a look at data parallelism in GNNs, model parallelism in GNNs, including pipeline parallelism, and we will then at the very end analyze a lot of different GNN models, trying to understand which ones are coming with more parallelism at the fundamental level, and we'll try to have a more broad outlook and what are the insights coming from how to execute these different models efficiently. In many parts, we are going to have to focus on getting the insights into, on one hand, what are the differences between parallelism in traditional deep learning versus parallelism in graph neural networks, and also in, as I mentioned, how much parallelism is there in different parts of the GNN landscape. So let's start with the recap of some important parts about GNNs. So at the very beginning of a whole GNN computation pipeline, we provide the input, which consists of the graph structure, and also with our coming with our input feature vectors for vertices and also possibly for edges. Right, then we run our input through a GNN model, which might include training and or inference, and we finalize with taking the outputs and running them through our downstream machine learning tasks such as classification or regression of edges, nodes, or the whole graphs. Right, we are going to use in the tutorial, we are going to heavily use the following symbol. This symbol indicates this picture indicates a single sample, and that example is a vertex with some dependencies going to other samples and together with our feature vector for this given sample. Right, so now let's take a look at different types of these samples that we have in GNNs together with their corresponding downstream machine learning tasks. So the first fundamental type are vertices that are samples, vertices that are dependent, right? So we can see these explicit dependencies between these vertex samples. And this setting we heavily use in GNNs, for example, to model atoms with example classification task being to predict the atom element, or for example, predict the atom charge as an example regression task. The next class of samples are edges, right? So the edges are also dependent via their neighboring vertices, and these edges can also become the first class citizens in our GNN pipeline, with an example being an atomic bond, for which we would like to, for example, run the classification task to predict the bond type, or run the regression task to predict the bond valence. Right, then we have the third class of samples, which are independent graphs. So this is a sort of a bit special type of samples in which a single sample is not really having any dependencies to other samples, but it may have some intra-sample edges, right? So an example, the obvious situation here is to have a chemical molecule being modeled by such a small graph, and an example classification or regression task being to predict some aspect of this molecule, for example, a class or a solubility, etc., etc. And finally, we may also have dependent graphs. Right? So we can think easily of scenarios where these small graphs also have dependencies between themselves. For example, a network of interacting proteins in which this network is a graph itself, and a single protein can also be modeled as a graph. Right. So why I'm mentioning all of these kinds of samples? Well, because the amount of parallelism and how we can run different GNN pipelines efficiently will heavily depend on what type of sample we are processing. Right, so now if we picture all of these samples, all of these classes of samples together, and if we compare it now to the traditional deep learning set of samples, the crucial difference here is the fact that we do have explicit dependencies between samples in GNNs. And even in a setting where we have independent graphs, even in this setting, these single samples, these individual samples have intra-sample dependencies that we also have to consider in some way, right? And this, as we are going to take a look and see in a couple of next slides, these dependencies make parallelism in GNNs really much more complicated than what we have in traditional deep learning. Okay, so that was the necessary recap. Now let's move to the first part of the presentation, where we are going to focus on the fundamental aspects of data parallelism in graph neural networks. So data parallelism can be split into two subtypes. On one hand, we have, as Torsten mentioned, graph partition parallelism. On the other hand, we have mini-batch parallelism that we can further categorize into independent and dependent mini-batch parallelism. Right? So this means that in this high-level GNN pipeline overview, we are now going to speak about parallelizing this pipeline, focusing on that part on the left, which is now not blurred, right? So this across the sample dimension. So let's start with graph partition parallelism, right? In this setting, we are going to focus on samples which are single vertices, right? So our setting is the common one where we have a large single graph that we want to process and run some predictions for, with one vertex being a sample. And now we would like to, we can split this graph across different parallel workers, right? So in all of the following slides, the color code is that different colors are corresponding to different parallel workers, right? So the main goal for using this graph partition parallelism is really because we would like to fit the graph somehow in our memory, and the graph is usually too large to be able to fit a single worker's memory, right? So that's why we split it across different workers, processing this in parallel, for example, across different memories, maybe across different disks. And the important thing is that every vertex and every edge in that scheme would fall into some partition, right? So we want to process the whole graph, which means that every part of it will sit somewhere in some worker's memory. Now, in dependent mini-batch parallelism, the situation is slightly different. So we again consider the same setting with one vertex being one sample, but now the reason for applying this parallelism is and this whole scheme is really to speed up convergence, right? So we use mini-batching to have faster convergence. And now one important thing is that a single sample may fall into more than one mini-batch, right? So that's one of the differences between mini-batch parallelism and graph partition parallelism, is that these vertices may be processed in more than a single such mini-batch partition. The other difference is that not all the samples may necessarily belong to some mini-batch, right? So this all depends on what sampling scheme we use, and we can easily imagine a scheme where some of these vertices will not be included in even a single mini-batch. And then we have something similar in the independent mini-batch case, right? So in that case, we deal with independent samples, for example, independent graphs. So one sample is now one of these graphs. And the reason for using this scheme is the same as in the dependent mini-batch parallelism, namely, we do this partitioning and this mini-batching to speed up convergence. We have similar features that on one hand, some samples may fall into more than one mini-batch, while not all the samples will necessarily belong to even one of the mini-batches. Right? And now if we now compare these two forms of data parallelism, we'll see the following differences. So the crucial difference between these two is the timing of updates to model weight. Namely, we use graph partition parallelism usually together with full batch training, because we process the whole graph that we can't fit into a single memory, which means that in that scheme, we apply the updates to model weights after processing the whole batch. While in the mini-batch parallelism, we update the weights after we finish processing a given mini-batch. Right? So that's one crucial difference in the design of the whole GNN pipeline for data parallelism. The second crucial difference is the reason for being incorporated. Right? So we incorporate graph partition parallelism to be able to fit the graph somehow in our combined memories, and we apply mini-batch parallelism to speed up convergence. And then the third crucial difference is the way that we do the partitioning, and especially the primary objective when partitioning. So in graph partition parallelism, we really focus on reducing the communication between the workers, right? Because this will improve our performance. In mini-batch parallelism, the way we partition is really related to how quickly we want to converge and to trying to make the statistical sampling as efficient as possible for that objective. And then the final difference are the inter-sample dependencies that may heavily impact the system design of the GNN pipeline for these two types of parallelism. Namely, in graph partition parallelism, there is almost always some dependency, and there is only no dependency if our graph is disconnected between the samples, right? But for mini-batch parallelism, in the independent setting, there will be no dependencies between the samples, which would, for example, enable us to simplify a given part of the GNN pipeline for a given independent mini-batch setting. So that was the high-level overview of different forms of data parallelism in graph neural networks. Now let's move to model parallelism. Model parallelism is more complicated and more interesting, in my view, than data parallelism. It splits into three parts. We have a thing called operator parallelism, pipeline parallelism, and DNN parallelism, where DNN stands for deep neural network, the traditional deep neural network setting. Right. So again, we take a look at this high-level overview of a GNN pipeline. So here we are going to speak about parallelizing this whole part, which is on the right side now, right? So the graph convolutional stage, the neural network, deep neural network stage, and the nonlinearity stage. And let's start with operator parallelism, which is something we apply to the graph convolutional stage. Here we can again see our single vertex sample. And in the first class of operator parallelism methods, we have a class called feature parallelism, in which we parallelize the processing of a single feature vector. Right? So it's a pretty fine-grained way of parallelizing the GNN computation. We do it by assigning different features to different workers. Then there is the other subtype of this class of parallelization schemes, namely the graph structure parallelism. And this is even more fine-grained because we are now parallelizing the processing of a single individual feature, right? So we can see here that in this feature vector, each single feature is being colored with these three different colors, which really indicates that each of the workers is now processing this feature in parallel, conducting, for example, some aggregation. So this is operator parallelism, a very fine-grained way of parallelizing GNN computations. The next that we are going to discuss is DNN parallelism, which is really about parallelizing the second part of this pipeline, of the single GNN pipeline, namely the dense layer. So here we also have two subclasses. We have on one hand DNN pipeline parallelism, in which so in this part, as Torsten mentioned, we have the MLP, which we are using to process the feature vectors of our vertices, or for example of our edges. And now we can see this MLP as basically the place that we could apply an arbitrary way of parallelizing a traditional deep neural network pipeline, right? And this is exactly what we are doing here. What we can do here, we can apply DNN pipeline parallelism, which would assign different workers to different stages of this small MLP, which sits within a single GNN layer. Or we could also apply a more general DNN model parallelism, in which we split the processing of this part more arbitrarily across different workers, resembling, essentially imitating the parallelization we would apply to a traditional deep neural network setting. Right. So this is another very fine-grained way of parallelizing the processing of graph neural networks. And then we have the third class of model parallelism schemes, which is called pipeline parallelism. It also has two subclasses, micro and macro pipeline parallelism. So let's start with the more fine-grained one, with the micro pipeline parallelism. So here we assign different workers to different stages within a single GNN layer, right? So in this example, one worker would be assigned to process the graph convolutional convolutional layer. One would be assigned to process the whole MLP, dense neural network part, and the final process could be, for example, be assigned to process the nonlinearity final stage of this GNN layer execution. It's also a reasonably fine-grained parallelization routine, but we can also now apply a more coarse-grained parallel approach, which is called macro pipeline parallelism, because now we could think of assigning different workers to different GNN layers, right? So here we can see that a given execution of a GNN has 3 GNN layers, and one worker is responsible for the whole first layer, the other is responsible for the whole second layer, and the third worker is responsible for processing the whole third layer, right? So this is a pipelined execution of a GNN computation across different GNN layers. And now there is one additional very interesting difference in the context of this macro pipeline parallelism between the traditional deep learning and graph neural networks. But basically, in traditional deep learning, and we can also have pipeline parallelism where we assign different workers to different layers. But the thing is that in traditional deep neural networks, we start with some data that we feed in through the first layer. And after we do it, we'll never really see the same data again, right? So we are then grabbing the outcomes of this first layer and proceeding to the next layer with some sort of transformed, modified data. And we continue like this, right? And this is in some way similar with GNNs, because we do the same with our input feature vectors. We feed them at the very beginning, and then we'll not really see them in the same shape again, because we are going to constantly transform them across our GNN layers. But at the same time, in GNNs, we also need to access the graph structure in our convolutional layers, in the convolutional stages, right? Which means that actually in GNNs, we do have to access the input data, because the graph structure is a part of our input data at different stages, not only at the very beginning, which now implies that we need to consider this aspect in the design of our, for example, software frameworks or hardware accelerators, because we have to have this efficient access to this initial graph structure at almost every stage of our GNN pipeline. Right, so now let's again take a look at the difference between traditional deep learning and GNNs in the context of parallelism. So on one hand, parallelism in GNNs is clearly more complicated than in traditional deep learning, right? And it's all because we have these dependencies between the samples in GNNs, right? So on the other hand, the second difference, the second high-level difference, is that we have new forms of parallelism in the GNN landscape. Again, because we have these dependencies. So for example, we have a dependent mini-batch parallelism, we have graph partition parallelism, we have graph structure parallelism. So these are the things that we don't really have in that shape in traditional deep learning landscape. So this means we have also potential for more interesting research and opportunities to provide more efficient pipelines, considering more of these ways of parallelizing graph neural networks. Okay, so this was the overview of different forms of model and pipeline parallelism. Now let's now take a look at how we can apply these different ways of parallelizing GNNs in order to formally understand what parts of the GNN landscape are coming with more or less parallelism. But for this, we need to first take a look at some way to formalize our GNN processing. So for this, we are going to focus on 2 ways in which we can formally describe a GNN model. So as we know, on one hand, we can describe a GNN model using the so-called local formulation, where we formulate a GNN model using functions that operate on single vertices and single edges. So this is the well-known mathematical expression for the message passing graph neural network generic formulation, in which we use the H symbol to denote vertex feature vectors. I is our vertex ID, and I are the neighboring vertices of the vertex I. Then we have the L, which indicates the GNN layer index. And then finally, what we have are these 3 functions: psi, aggregation, and phi. And these functions specify the details of the model, right? So we provide once we provide the specific expressions for these functions, we have a concrete GNN model that we can use to run our predictions. But we also have another way to describe graph neural networks, graph neural network models, specifically the so-called global formulation. So in these formulations, we construct a model using operations on matrices that group all the vertex and edge-related vectors. Right? So this is an example generic formulation for this global view of graph neural network models. Again, we have L, which indicates our layer GNN layer index. Then we have the age matrix, which we use to group all the feature vectors of vertices. And then we have also the adjacency matrix, which we use to describe the structure of our graph. And finally, we have also model parameters grouped in some parameter matrix. Right? And then what we also have are certain functions that we need to specify to provide the model details, right? So we can apply some transformation to the adjacency matrix, and then we can optionally provide an element-wise product with some more complex expression hidden here within these two brackets that could make the model, for example, maybe more powerful. So we'll see many examples of such models in the next couple of slides. Now, just one important notion is that these formulations are not really fully equivalent, which means, so what I mean here is that some GNN models only have known local formulation, and vice versa. We also have models that we only describe using the global formulation and not really the local one. Right, and now I'm going to use these formulations, these local and global equations for local and global GNN model formulations to formally analyze the amount of parallelism in different GNN models. So let's start with local formulations. Here we can see a cheat sheet showing the general equation and also the high-level overview of a single GNN layer. Right, and now I'm going to use a couple of symbols, namely symbols that illustrate vectors and communication of these vectors. So this is this red color that indicates a vector that we are communicating somewhere, and the green color and the green vectors, which indicate a vector on which we are doing some local computation, indicated with this circular arrow, without any communication. Right. So now let's take a look at a single GNN layer in more detail through the perspective of this local GNN model. Right. So as we know, we have a couple of phases there. One phase is the scatter phase, which is a part of the phi function in this general, of the psi function in this general local formulation. In this phase, we have our example graph here, consisting of 4 vertices and 3 edges. And now each of these vertices has some feature vector, right, that we indicate here with these red vectors here. And in this phase, we are now sending these vectors along our neighboring edges towards in order to produce some new output in the next phase, right? So in this phase, in the scatter phase, we are sending these vectors along the edges, right? And we can do all these sends in parallel. And then the second phase, in the update edge phase, we are using this issued vectors in the previous phase to conduct some local computation and to generate new edge feature vectors, right? In this phase, we don't really do any communication, and we can also apply all these changes in parallel. In the third phase, the reduce, or also called aggregation phase, we are now gathering the outcomes of this previous phase, and also we are gathering the previous edge feature vectors and reducing them across the edges, right? So for example, for this one vertex here on the right side, we only need to grab its adjacent single feature vector of the corresponding edge, but also of its adjacent neighboring vertex, right? So we only need to reduce two feature vectors in this phase for this one vertex here. But then for the central vertex, we need to conduct a reduction over many different vectors belonging to the adjacent neighbors and belonging to the adjacent edges. And in the final phase, in the update vertex phase, which is forming the final function, the phi function, we then run some local computations, for example, an MLP or linear projection on the output of the third phase, on the vertex feature vectors that we derived in the previous phase, in the previous reduction phase. Again, we can apply the computation in this, we can parallelize the computation in this phase in full scope. So we don't really have to synchronize with anybody else. We can run all these changes locally in parallel for every vertex. Right, and now we could think of applying different forms of model parallelism to these different stages. For example, a straightforward approach for parallelizing these stages in the context of what we said before is to apply different forms of operator parallelism to stage 1 and stage 3, and different forms of GNN parallelism applied to stage 2 and stage 4. Now let's delve a bit into the formal foundations of parallelism in the GNN models expressed with local formulations. Right. So for this, we are going to use a certain theoretical framework known in parallel computation called the work depth. So in this framework, we picture any computation that we have as an execution-directed acyclic graph, EDAG. Right. So this graph here illustrates some arbitrary execution that we may have in our GNN pipeline. So this can be something completely arbitrary. What is important is that now these circular arrows indicate some simple operations, for example, summation or multiplication of some arguments, and then these arrows, these straight arrows indicate dependencies of some operations on the previous operations. Right, so we can use this formalism of EDAG to model essentially any type of execution. And now there can be two properties of such an EDAG. So one property is called work, which counts the total number of such operations that we have in this EDAG, and the second one is called depth, which really indicates the longest chain of sequential dependencies in a given EDAG. Right. So on one hand, the goal of when designing an algorithm, a parallel algorithm, would be to minimize the work. Right. On the left side, we can see here now some example amount of work, which is quite high, and we would like to minimize this amount of work, namely the total number of operations in a given EDAG. And the same for depth, right? So we would like to also minimize depth to remove or to minimize our sequential bottlenecks in a given execution. So in this particular example, we can see that there is a certain part of this DAG which is really long and would become a bottleneck for our computation. And in this view, we would like to minimize it by, for example, somehow eliminating this path, the subpath of this execution, and have something which comes with much lower depth. Right. So an important takeaway from that slide is really that we have these two properties of a given execution, but these are also properties of a given, for example, GNN model, like work and depth. So what is work? What is depth? Work will tell us about the total number of operations we need to conduct in a given GNN model execution, and depth would be the sequential bottleneck. So basically, what is our bottleneck beyond which we can't really go? We can't really overcome this bottleneck, regardless of how many processors we would be throwing at a given GNN execution. Right, so I'm going to use the following notation in the subsequent analysis. N will indicate number of vertices. It's the standard notation we use in our landscape. M is number of edges. K is number of features. Big L is a number of layers in a GNN, so number of GNN layers. And D is the maximum degree in a given graph. And also, we are going to use a couple of different symbols to indicate different mathematical objects. So this dot will indicate a scalar. This will indicate a vector, a dense vector, of dimensionality being the number of features. We are also going to use quite often the symbol of a small dense matrix with number of dimensions being somewhere in the order of the number of features. We are also going to use the tall and dense matrix. So here the small dimension is the number of features, and the big dimension is the number of vertices. And finally, we are also going to use the symbol of a sparse matrix with the number of dimensions being the number of vertices. Right, and then the number of non-zeros in this big sparse matrix is the number of edges. Right, so this is really our adjacency matrix, or something based on the adjacency matrix with the same sparsity pattern. So let's start with analyzing formally how much parallelism is there in the very seminal graph convolutional network model. Right. So first, let's disseminate this GCN model into the fundamental functions that form the local formulation. Right. So first we have the psi, which is really just the multiplication of the feature vector of a given neighbor with the normalized product with the inverse of the root of the square root of the degrees of that vertex and its neighbor, right? So it's really our matrix normalization that we are applying at the beginning of the GCN model, right? And now the important thing is the compute pattern of this function execution. So in the compute pattern, this operation is really equivalent to multiplying a scalar, some scalar number c, with a dense vector that has the dimensionality of the number of features. Right, but then we also have the two other functions in the local formulation, the phi and the aggregation, the aggregation symbol, and we treat them together just for simplicity. And they can be seen as they can be written as this expression here. So we have our psi that we wrap here, and then we conduct the aggregation over the neighborhood of the vertex I, and finally we multiply the outcome with the parameter matrix using a matrix vector product. Right. So here really the fundamental compute pattern is doing some summation of the dense feature vectors, summation that may span up to d different vectors, right? So we may be summing up to the maximum degree number of such vectors, and the outcome is multiplied by a dense matrix of dimensionality k times k. And now what's the work and depth? Right, so I'm not really going to derive this really step by step, but this model is anyway very simple. So we can probably already see that the work for this operation here, for the psi operation, is really O of k, right? So the work is really proportional to number of our features, and depth is really O of 1, because so this operation is really trivially parallelizable, right? We can do this multiplication completely fully in parallel, and this means the depth is very nice. It's O of 1, so we can yes, so this operation is not really any bottleneck for our parallel execution. Now for the second part of this model, for the phi and aggregation, here I'm going to derive the final work and final depth for the whole single training iteration. So this is here we are going to consider all of these executions of psi together with the aggregation and the multiplication across L different GNN layers. Right, so we can see that the work here is really a sum of two terms. In one term, we have number of GNN layers L times number of edges in the whole graph times number of the features. In the second, we have again number of GNN layers times number of the vertices in the graph times the square of the number of features. Right, so this is really the work that we have that we need to dedicate. It doesn't really look horrible, but it also doesn't look like something very, very, very low work. Right, so we have this square number of features, which may actually get quite large. So we may be actually a bit worried about how much work we need to throw at this model. But then what it turns out that the depth is actually very nice. So depth is really the sum of the two terms. In each term, we have linear number of GNN layers L, and then we have always the logarithm of something. And on one hand, we have the logarithm of the maximum degree in the graph. On the other hand, we have the logarithm of the number of features in our vectors. Right, so this is actually implying that depth is quite low, because our only the major bottleneck that we can see here is the number of GNN layers. Right, this is only the linear. This is the only linear term in this equation. All the others are logarithmic, and also k we know is quite small in most cases, which means logarithm would be even smaller. Right, so that means that despite having some reasonably high amount of work, the depth is going to be actually quite low, and we will not really have a major sequential bottleneck in the execution, perhaps except for the number of GNN layers. So that's our main conclusion for the GCN model. Now let's take a look at something a bit more complicated. Let's take a look at the graph attention network model. Here we have again a way of disseminating this model through the local GNN model formulation formalism. Right, so we have the three functions again, the psi, the phi, and the aggregation function. And here it turns out that our first function execution that we need to conduct for every edge between any vertex I and j is actually quite complicated. Right, this expression actually looks a bit complex. This is, I mean, what we are doing really here is the well-known part of the GAT model. So in this model, we need to conduct the attention over every neighbor of every vertex, and then we need to normalize it with softmax. That's really what this equation is about. So let me allow me not to go into details of what this expression actually is doing, because that's not really the most important part. That's really the established GAT model expression. What is really important is the compute pattern of this expression, right? So here we also have the expression for the phi and the aggregation, and also the corresponding compute pattern. And you can see that the compute pattern for the psi function is also quite complicated, right? So we need to do all these matrix multiplication, matrix vector multiplications, concatenations, dot products, and exponentiations. On the contrary, the aggregation and the phi are actually quite simple. So once we compute all these attention scores for every vertex, for every neighbor and every vertex, we just need to plug them in here in this expression and conduct the final aggregation, followed by multiplying by the parameter matrix. Right, so the corresponding compute pattern is also not very complicated, but this one here is actually quite complex. Right, so now if we analyze work and depth, again, I'm not going to do this really step by step, but this is actually quite simple, because all you have to do is to identify the most time-consuming, as it's the big O notation, all you have to do is to identify the most time-consuming operations and really consider them as the major culprits of that add up to the work. So it turns out that the work for the single execution of this function here is really max degree in the graph times the square of the number of features. So it looks actually pretty large, right? Because now we probably think that we need to conduct this for every edge in our graph, which would add up to a very large work finally. And this is the case, yes. But what is important is that actually this execution is at the same time very nicely parallelizable. So despite having all these different elements adding up to a lot of work, we can run this thing in depth being only log k plus log d, which means that's not really going to be a major bottleneck in our computation. And then once we wrap together all these executions of the psi and plug them into the final expression together with the aggregation and the phi, our final work will be, as you probably expected, quite high. So this is going to be proportional to the number of GNN layers as before, number of edges as before, but then also the max degree and the square of the number of features, and then plus L times n times k squared as before. Right? So this is actually a lot. But again, the depth of the whole computation, in that case, single training iteration, is again only linearly dependent on the number of GNN layers. Right? So all the other factors are being logarithmic. So again, this L is kind of maybe worrying us, but this D and K and the rest of these executions of this psi here are not that bothering. So yes, the final conclusion from that slide is really, even for a complex and very work-heavy graph attention network model, we also have plenty of parallelism that we can apply. Now what we did was to conduct such an analysis for many different GNN models, not just GCN and GAT. So we summarized this analysis in this table here. One row of this table is going to correspond to a single GNN model formulated using the local formulation, right? So we can see GCN here, we can see graph attention here, we can also see others. We can see monad, we can see vanilla attention, comnet, and many others. Right now we have in our paper we have uniform formulation, like we have formulations using uniform notation for these different models to simplify the analysis. So these formulations are not that greatly important for this presentation. So let me indicate this with this white background. What is really important is that we can categorize these different GNN models into three classes. We can categorize them into CGNNs, so-called convolutional graph neural networks, into AGNNs, so these are attentional graph neural networks, and into MPGNNs, message passing graph neural networks. Right, and as you probably know, these classes differ in the output of the psi function, right? So for the CGNN models, this output of the psi function for these models is a static scalar. For the attentional GNNs, this output is a learned scalar parameter, and finally for MPGNNs, this output is a vector, it's an arbitrary vector. Now what we did was analyze and derive the compute pattern for each of these models, right? So we again can see this complex compute pattern for the graph attention and the compute pattern for GCN, but also all the others, right? And we use this compute pattern to derive the work and depth of single execution of this psi function here, right? And then now let's take a look at some of the insights we got in the process. So what is quite obvious is that AGNNs and MPGNNs, so these two classes here, are coming with much more complicated compute patterns than CGNNs, right? So this is pretty obvious because CGNNs are essentially just summing. So the execution of psi is essentially just either multiplying the vector by a scalar or simply taking this input vector as it is. And this also kind of can be visible by work and depth, because for CGNNs, work and depth are almost always O of 1. So we either don't need any work and any depth, or we just need O of k work for GCN and maybe some other models like this. And then it turns out that nearly all of AGNNs and MPGNNs have work and depth, which are so have O of k squared work. So work is proportional to the square of the number of features, and logarithmic depth, logarithmic in the number of features of a single vector. This is the case even for the most computationally intensive graph attention model that we analyzed, right? So this means that all of these models, despite maybe having quite some amount of work, basically all of them are nicely parallelizable. And as you can also see, most of them, basically again, except for graph attention, their depth is logarithmic in the number of features, which is even better because number of features is usually lower than for example, the maximum degree in the graph. So this is going to be a minor bottleneck in our executions of the single function psi, right? So we again always at this moment speak about the function psi. But now, once we compute the psi's, we need to sum them using or aggregate them somehow using our aggregation, right? And for this, we realize that aggregation is almost always an operation that is commutative and associative. So this can be a min, max, or a plain sum. That means that essentially all of these aggregation schemes can be executed using established parallel tree reduction algorithms. And essentially these algorithms, all of them take logarithmic depth in the maximum degree in the graph and work which is proportional to the product of the number of features and the number and the max degree, right? So that also means that aggregation may be actually a bigger bottleneck in depth in many of these models than, for example, the psi function, because our maximum degree in the graph is usually bigger, at least in the current workloads that we can see, is usually bigger than the number of features, right? So this logarithmic, this log d in depth of the aggregation may actually be in practice bigger than log k that we see in the depth of the execution of the psi function. And finally, we also have the final function, the phi, together with all of the previous ones. So we would like to now try to see the parallelism in the phi function, but also how do all these functions add up together the final work and depth scores for these different GNN models. So again, we have a similar table as before. One row of this table is one GNN model. Again, we have these three classes that we saw before: CGNNs, AGNNs, and MPGNNs. And again, we derive the formulation for the phi function. But again, these formulations are not really important in this presentation, so we can check them in the paper with our uniform notation. Here, what is important is, again, the compute patterns that we have for each of these models. So here you recognize the compute pattern for the GCN model. It's again like the summation of these different feature vectors multiplied with the outcome being multiplied by some dense parameter matrix. And this pattern is actually very prevalent across different models, right? So we can see that this summation of feature vectors and then the multiplication by the parameter matrix is the dominant compute pattern in these different GNN models. In some models, there may be no such multiplication, but maybe just a plain summation. In some other models, there may be a bit more complicated compute pattern where we may, for example, have to do some concatenation, but they don't really change primarily the primal foundational compute work and depth properties. So if we now take a look at these results for these different models, we'll see that the depth of a single GNN layer is almost always logarithmic. So this is actually a nice outcome because it indicates that in all of these models, not only the execution of a single psi and a single aggregation, but really the execution of a whole of a single GNN layers is always is always logarithmic in depth, which means that a single GNN layer does not pose too much of the bottleneck for our potential computations. On the other hand, depth of one GNN whole training iteration is usually linear in the number of GNN layers, right? So that's something we can't easily avoid. We will always have this number of GNN layers that we need to provide and interleave with our nonlinearities, which is why we can't really easily alleviate this, but we'll take a look a bit later how we can actually do it as well. The work for different models varies, so the total number of operations we need to apply varies across different models, being the highest for the graph attention, but also reasonably high for other MP-GNN models, right? So we can very often see the square of number of features that we need to throw in to compute, to process a given GNN model. So now let's take a look at the global formulations, right? So with this slide, we finish our local formulation detailed analysis. The high-level outcome is that despite their differences and how their compute patterns look like, all of these models are pretty much very nicely parallelizable without major bottlenecks in the depth, maybe having high amount of work, which can be, however, alleviated by throwing more compute resources at them. Right now, let's take a look at how it looks like for GNN models that we formulate using the global formulations. So let's start with the simple model, the GCN model, which we can not only formulate using local, but also global formulations, right? So we can see this model here at the top right. In this formulation, we, to get the feature vectors in the GNN layer L+1, we need to multiply our adjacency matrix times the feature matrix that groups all the feature vectors in our given L iteration times the parameter matrix, right? And this corresponds to our illustration here that kind of illustrates this in more detail. We have the sparse adjacency matrix times the feature matrix times the parameter matrix, right? With the big dimensionalities indicating the number of vertices and the small ones indicating the number of features. Right, and now this highlighted row here corresponds to the neighbors of a specific vertex V, right? For whose feature vector we are now computing. On the other hand, this highlighted column corresponds to the specific feature F that is being computed for this vertex V, right? So one column of this H matrix is a single feature, one row of this A matrix is the neighborhood of a given vertex, right? And now we realize that I mean, we know this, that different parts, different products in this matrix multiplication chain correspond to different parts, different phases of our local formulation. So, for example, the product between the adjacency matrix and the H matrix is our reduction from the local formulation, and the product between the H matrix and the W matrix is the fourth update vertex phase, essentially the phi function from our local formulation. Right. And now, in terms of parallelization, we can process each of these rows in parallel. So we can consider these rows of the adjacency matrix in parallel, which really corresponds to considering different vertices in the local formulation in parallel. At the same time, we can also consider each of these columns in parallel, which would correspond to parallelizing across the feature dimension, processing different features in parallel. However, this moment where once we combine A with H, we need to synchronize, because once we have partial feature scores for a given vertex, we need to sum them up. And in this moment, we need to conduct some synchronization, which is really our log D bottleneck, our logarithmic bottleneck in the depth of the reduce function that we have in the local formulation. We also have such analysis for more models. For example, for the vanilla attention model, which is very similar to the GCN model, we can see this the expression for the vanilla attention here. So our A is again the adjacency matrix. On the right side part, we can see again the product with the feature matrix and then the parameter matrix. But then what is different is this part in the middle, right? So we also have to conduct the element-wise product with a result of H matrix times its transpose, right? So this is really the linear algebraic way of writing that we need to combine. We need to compute the attention score for every edge, and then apply these scores to our adjacency sparse matrix, right? So this corresponds to our picture here with these parts that we know from the previous slide, and now the new parts that correspond to the edge attention scores that we have to compute for every every edge. And these also these operations now correspond to the first and the second stage of the local formulation pipeline, right? So we have the parts, namely the element-wise product of the adjacency matrix and the outcome of the h times its transposed corresponding to the scatter function, and the update h part, which really corresponds to this product of these two matrices here, right? But now again, what is important is the parallelization. Right, so the highlighted columns here in this picture, in the central part of this picture, correspond to two feature vectors we are going to use to derive an attention score for a given edge. And now, in terms of parallelizing, on one hand, we can apply all the ways of parallelizing this as we did in the GCN model, and more. Right. So on one hand, we can now apply all these element-wise scores here, element-wise products between the adjacency matrix and this dense matrix here. We can apply them all in parallel, and the same for these dot products between these corresponding feature vectors. Right? We can now apply the dot product computation fully in parallel to compute the edge scores fully in parallel for every edge separately. Okay, that was quite intense. So now let's take a look again at a bit more high-level summary. So what we have here is a similar table that we had for the local formulations. One row of this table corresponds to one specific GNN model. We again have some models. So here what we can see are some models that we also know from the previous table that we had for the local formulation. So this is like GCN, GIN, ComNet. We analyzed this model also before and using work depth for the local formulations. We also have now their algebraic formulations in the global sense. What is important is that all these models use the first power of the adjacency matrix in their expressions, right? So we have this adjacency matrix in the first power somewhere in these formulations. And this is why we also can call these models linear models, because they use the linear form of the adjacency matrix. But then there are more models in the whole graph representation learning landscape, other models in which we use the adjacency matrix in a more complex form. So in these models like DeepWalk or ChebNet or Node2Vec, we use some natural power of our adjacency matrix. And this is also why we call these models polynomial models, because we use some polynomial power of the adjacency matrix in the expressions of these models. And then we have also the third class, which is even more generic, in which we use some rational power of the adjacency matrix in the mathematical formulation, which is why we also call these models rational R. Right. So this is what we know is out there. This is the well-known shape of the graph representation learning landscape. We have these three classes: linear, polynomial, and rational, that we all can formulate using global formulations. And now again, the question: how do they fare in our parallelization analysis? What is their work? What is their depth? Do we have any patterns between these different models? Right. So again, we provide the compute patterns of these different models. Again, I'm going to skip the details how we derive it, but it's actually quite straightforward. Again, you identify the most important operations and just picture them using the matrix, the right matrix symbols. And you can see that in the linear models, the prevalent operation is the product of the sparse adjacency matrix times the tall feature matrix times the parameter matrix, sometimes with some variations, like, for example, having the vanilla attention computation or having a series of small parameter matrices if we have, for example, a full MLP applied at the end of the given layer. Right. Then for polynomial matrices, we at some point have to sum our or apply some higher power to our adjacency matrix, which is higher than the power 1. Right. So we, for example, in DeepWalk, we need to sum a series of our adjacency matrices to rise to different powers. Right. And then we also at the very end also have to multiply by the feature matrix and by the parameter matrix. And then in the rational models, we may have to raise our adjacency matrix some more arbitrary power, for example, -1. Right. And now we also provide the results for work and depth. Here again, picture the results for one whole training iteration or inference. The conclusions are that depth of a single layer in linear models is always logarithmic. So good news, we can parallelize these models nicely. For polynomial models, depth of a whole training iteration is also logarithmic. So in these models, we don't really have, usually don't really have nonlinearities between layers. So we don't really have this notion of GNN layers. Instead, to gather the information about the more remote parts of our graph, instead of doing this layer-wise propagation, we raise the matrix to the higher power. But as we don't really apply these nonlinearities in between, we can nicely parallelize raising this matrix to the higher power, which results in having logarithmic depths for the whole training iteration. And similar outcomes for the rational models, despite having the most arbitrary formulation, we can actually compute these models in square logarithmic depth. So it's not exactly logarithmic, but it's almost logarithmic, and it's actually also in practice quite parallelizable. So now we have this very broad view on both local and global GNN formulations, right? So we have this, again, the cheat sheet, we have the local formulation on the left, we have the global one on the right. And now what is their differences, right? So, so on one hand, some models have both formulations. For example, the GCN model can be expressed easily in both. That's not always the case for many of these models. But for such models like GCN, they have at the fundamental level the same amount of parallelism because they come with the same work and the same depth, right? So regardless if we write now GCN in the local formulation or in the global formulation, the amount of parallelism will be exactly the same in both formulations. And that now translates to more practical outcomes in how we actually implement this, right? Because these formulations, behind them, there is hidden a whole world of different ways of implementing these models, right? Because now local formulation would be implemented differently from a global one, but the amount of parallelism in both implementations would be exactly the same. However, there are also now more fine-grained differences because we use different compute kernels in these different formulations. So in local formulations, we use often kernels like concatenation of two different vectors, element-wise product of two vectors, summation of vectors, dot products, maybe a dense matrix vector product. But the important thing is that in all of these kernels, dimensionality is always k, number of features, which is not very large in practice compared to, for example, number of vertices, right? But in global formulations, what we use are different kernels, which are usually much bigger in scope. So these are also dense matrices, for example, matrix times its own transpose, or the product of two matrices. One of them may be having a large dimension being equal to the number of vertices, but also we use sparse matrices, right? So sparse adjacency matrices, or even powers of these matrices. And now it looks like these computations are actually different in the context of these details. And this is really the case because they would now come with potential for different optimizations. The global formulations come with potentially more opportunities for vectorization, right? Because we have basically more numbers we could try to vectorize. Dimensions are bigger in many cases, which is why we could apply vectorization probably more often and more successfully than in local formulations. But in local formulations, we also have some advantage, namely potential for more flexible scheduling, right? So as we deal with smaller kernels, it may hurt our vectorization routines, but at the same time, we could now more easily schedule different kernels because now they are smaller in scope, smaller in the amount of work and that we have to apply to them, which means we can schedule them more effectively across fine-grained compute resources. Finally, let's also take a look at the difference between linear versus the polynomial or rational formulations, right? So this is fully within the scope of global formulations. As you remember, we have linear ones where there is the first power of the adjacency matrix being utilized, and then we have polynomial and rational ones where we may have more complex powers. For example, in the node 2 vec, we have the second power of the normalized adjacency matrix. In PPNP model, we have the -1 power of the adjacency matrix at some point. Right, and they also offer parallelism, right? So this is the other takeaway. We can also parallelize them at the fundamental level very nicely with log n depth for the polynomial models and log square n depth for the rational models, right? And this is really because while the L vanishes, they require deriving a given power of the adjacency matrix, which complicates it a bit, but at the same time, it's really a way to be able to parallelize them more effectively. However, as we don't really have these nonlinearities in these formulations very often, this means that they may also come with some loss in the representative power, right? So this is actually a trade-off. Now we can use these models maybe more willingly because we could run them faster, but at the same time we may deal with some accuracy loss in our predictions. So now let's move to the final part of this tutorial. I'm going really to focus here on this one aspect that I mentioned a couple of times during the slides. So I used to say that we have this L term, which is number of GNN layers, and this term sounded a bit annoying, right? Because we had many times that there was this final depth, which indicates our sequential bottleneck, and in most of these models, this depth was linear in this L, right? So we could not really reduce the sequential bottleneck of this L with this previous analysis. But can we somehow alleviate this? Yes, the answer is that we can actually do it. And we can do it in a couple of different ways. Let's just take a look at one class of schemes that we can now grab to actually make this L in practice lower. So I'm not going to show you now any asymptotic advantages. I'm only going to show you a path to actually doing this more effectively in the future, because this is what I'm going to introduce now is in most cases actually not yet explored in the context of the practical implementations or outcomes. So what I'm going to discuss are asynchronous graph neural networks, in which we introduce some staleness in the formulation and or in the execution to get better throughput, and in practice lower this L term. I'm going to use the following symbols and colors. So colors in that case are going to indicate different layer stages, right? So this will partially overlap with our parallelization of the GNN layer. So red color will now indicate the sparse graph operation and the worker which is conducting the sparse graph operation. The green color will indicate the dense neural network operation, MLP in that case, and the blue color will indicate the nonlinearity, such as ReLU, and also the worker doing this stage. Next, I'm going to use different lengths of blocks. So the length of blocks indicates duration of a given stage, right? So this the shorter the block, the shorter the given stage of a GNN layer will run. The faster it will run, sorry. Now, different shades of colors will indicate different GNN layers. So in the following example, we are going to take a look at 2 layers of a GNN execution, both in the forward propagation. The light shade colors are going to be layer 1, and the deep shades will be layer 2. Now, important thing, every color and every shade is a different worker, right? So we are going to see 2 different layers, each layer having 3 stages, which means 6 workers in total. And finally, the P1, P2, and P3 symbols will indicate different graph partitions, right? So we are going to set this asynchronous GNN execution setting in the context of graph partition parallelism. So asynchronous GNNs, we could now apply this asynchronous execution both to micro pipeline parallelism, where you probably remember we assign different workers to different stages of a single layer, but also to the macro pipeline level, where we parallelize across different GNN layers, right? This means we could now have 4 different combinations. So let's start with the basic setting, where we don't have any asynchrony at all. We are going to see here an example of a synchronous micro pipeline combined with a synchronous macro pipeline execution. So in this plot on the x-axis, you can see the time, right? So we are proceeding with our computation from left to the right. The y-axis is the number of is the specific device or a worker, right? So this row here corresponds to worker 1 in layer 1. This row here corresponds to worker 2 in layer 1. This row here corresponds to worker 3 in layer 1, right? And the same for layer 2, right? So, and then we have this line in the middle, this dashed line, which indicates inter-GNN layer synchronization between these 2 layers, right? And then we can see that in this fully synchronous execution, first thing, the neural operation executed by worker 2 must wait for the full finishing of the execution of the red convolution operation done by worker 1. Then nonlinearity have to wait for finishing the neural execution assigned to P1, to partition 1 and worker 2. Right? Then we have to wait. Once we finish layer 1, we really have to wait until the whole computation of layer 1 is finished before we can start processing layer 2. Right? So this is full synchronous execution in both micro and macro pipeline. Right? Then what we can do, we could introduce asynchrony at the very beginning in the micro pipeline level. right? So here, what it means is that we still have this inter-GNN layer synchronization because we have still synchronous execution in the macro pipeline, right? So we don't really do any asynchrony across the GNN layers, but we do asynchrony within a single GNN layer at the micro pipeline level, right? So that means in practice that the worker 2 can start processing the neural operation right after the corresponding operation of a given graph partition is the convolution operation of a given graph partition by previous worker is being finished, right? So that means that in this moment we do introduce some staleness because this neural operation is going to only consider the finished results of a single graph partition, and it will not wait for finishing the results of this partition 2 and partition 3, right? So that also means that we may also at this point have some staleness in our outcomes, right? Then we do the same in layer 2. Third, the third combination we may apply is having the micro pipeline synchronous, but introducing asynchrony at the macro pipeline level, right? So that means that in the micro pipeline, the worker 2 still has to wait for all the graph partition to finish their graph convolution stage before grabbing that outcomes for the neural network stage, the dense part, right? But we don't really have this synchronization between the layers no longer, which means that we can now start processing again the corresponding computation belonging to layer 2 as soon as we finish processing nonlinearity of the first partition of the previous GNN layer, right? So that means we again have some staleness, this time of a different type, because we don't really wait, for example, to finish this neural network operations in the previous first layer, but as before, we have we can see some improvements in our time execution, right? So this is why we do it is because on one hand we can improve the throughput, which translates to having faster execution, right? So before, at the very beginning, we saw that in a fully synchronous execution we had long timeline that it took to process these two layers. Then introducing asynchrony in one part in the micro level or in the macro level reduces the latency of the whole execution. And then at the very end, we can do the full asynchrony in the micro pipeline at the same time with the macro pipeline, which further improves the throughput, further reduces the latency, but makes this execution potentially even more stale, right? We may see even more staleness here. And then at the very final step, we could even think of removing the synchronization at the very end of the forward propagation pass and do the asynchronous pipelining with the backward propagation pass to have a fully asynchronous execution, also considering forward and backward propagation pipelining, right? Again, having much higher throughput, but at the same time having even more staleness, right? And then what we show in the paper is that we can actually also formally describe it using the message passing graph neural network formulation. Right, so here we have again our cheat sheet, the MP-GNN formulation that we know from the previous slides. And now one way to extend this formulation towards asynchrony is to explicitly consider these graph partitions, right? So at this moment, we still don't have any asynchrony introduced. I'm just only introducing the graph partition explicitly into the MP-GNN formulation, right? So we can see this by splitting the aggregation function across two types of neighborhoods, right? So now each one of the vertices may have neighbors in its local partition, but also may have neighbors in some other remote partitions, right? And now we can consider this explicitly at the model description level here by splitting this aggregation function into these two parts, right? In one part on the left, we aggregate over feature vectors in our local neighborhood NL. On the right side, we do the aggregation in the remote across our remote neighborhood, so the remote neighbors that are maybe in other graph partitions, right? So of course these two must, we must be able to compute their union, and this union must be the initial neighborhood of vertex I, right? And then once we have these outcomes of these two aggregations separately for the local and the remote ones, we can conduct their final aggregation, so aggregate them together to the final score, right? But then what I also and then we can further extend this towards the asynchronous execution, right? So for this, again, let's take a look at the previous the equation here. So here we can see we have two indexes now. One, we have this L, which as before indicates our GNN layer, but T now also indicates the training iteration, right? So now we explicitly consider both the training iteration and the GNN layer. And in this middle equation here that I just explained before, we can see that this is still synchronous execution because the state of our feature vector in, for example, layer L and training iteration T is based on the feature vectors of the same training iteration T, right? So T is also here always the same, and also on the L-1 GNN layer. So we do as we did before. We grab the feature vectors from L-1 GNN layer, and we use them to compute the feature vector in the next GNN layer. Now moving to the lowest to the bottom equation, this is exactly here how we introduce the staleness, how we can do it at the level of the model formulation. So we have now, for example, here in this L iteration index, sorry, in the GNN layer index, we have parameters that introduce the staleness. So for example, here this big L with phi is a user parameter that specifies how far into the future, in the worst case, we can to fetch the feature vectors from some iteration from some GNN layer which is far behind in the computation, right? So if this L phi is now, for example, equal to 2 or to 3, we would be using the feature vectors from 2 or even 3 iterations before, right? Which really would make the execution stale. And the same for training iteration, right? So we could now apply this concept both for the GNN layers and for the training iterations. Right? That's really the way how to formally describe GNN models, asynchronous GNN models at the model description level. Now, the interesting research direction would be try to devise GNN models, like the concrete models that actually apply this in practice and see how they fare, both in terms of their predictive power, convergence speed, but also performance, throughput, and latency. You can check the paper for many other details that we analyzed. On one hand, we provide many more details about the mathematical formulations of GNN models. We actually have even more details, and especially their correspondence to the programming paradigms, right? So we now in GNNs, we now have on one hand mathematical formulations, the global and the local formulations, but also we have our programming paradigms that there are a couple of these different paradigms, many of them basing on scatter, apply edge, aggregate, and update vertex programming kernels, but also with others having even more sophisticated ones. And we provide analysis into how these two correlate with each other, again, in the context of parallel execution. Right, and we also provide more details about data parallelism, specifically the neighborhood explosion phenomenon that was nicely described in the previous tutorial. The way we can partition the graphs now, so we can also apply more sophisticated schemes to the way that we partition the graph in the graph partition parallelism, and also even more effects being analyzed together with their work and depth analysis. Then we have also details about asynchronous GNN computations, the context of computing gradients. So we can also introduce asynchrony in computing the gradients. You can also check this in the paper. And then we use all these insights we got to analyze the parallel design of different existing GNN frameworks and accelerators, right? So we analyze what is the support for parallelism introduced in different frameworks, different accelerators. For example, do they support data parallelism? If yes, which mode? Do they support model and pipeline parallelism? And this, for example, could be used by to maybe disseminate like ways of parallelizing which are more powerful. So analyzing different frameworks with their respective design differences, trying to identify the most advantageous way of parallelizing, combined with the applicability into the GNN model domain. And finally, you feel free to check our how we actually apply some of these insights from this investigation into devising new GNN models that we use to solve problems such as motive prediction, or how we actually apply some of these comments into more system design aspects of GNNs, for example, combining GNNs with graph databases. Thank you for your attention, and please provide the feedback in the following form. And now we can take your questions together with Torsten.
Yeah, Wenchi has a question.
Yeah, so thanks for the very nice and very comprehensive presentation. And as you said, there are many ways to parallelize the GNN. And is there a comprehensive study about how this different parallelism will affect the training time, the accuracy, and so forth? Or do you plan to do some research about that?
We plan to push this and to analyze this better together with developing new systems based on these insights.
Okay, thanks.
But just one like the follow-up on this question is that the prevalent way. So I would say at this point it's really not about because like the development of these frameworks is still in its somewhat early stage. And what you can see is something you would expect is that the simplest forms of parallelizing are being used more frequently, right? So what we saw was that most of these frameworks actually apply data parallelism either in the shared memory setting or in the distributed memory setting, but really data parallelism is the prevalent way of doing this. On the other hand, what you would also expect at this stage of development is that the most complex aspects are still not really touched, right? So for example, while there are a couple of designs that do macro and micro pipeline parallelism, but only a few, there is very, very few that really touch on asynchronous parallelization, right? So this, I didn't really see much in that direction because probably it's the most complicated, but also would be interesting to analyze now how this works in practice.
Yeah, definitely. There are many research questions out there. Thanks a lot.
Yeah, one addition is also like once we scale graph neural networks to extremely large data sets and larger models than we do today, then we will require these other forms of parallelism. So for these small models that we are looking at these days, it's not yet required, but I'm expecting that those will scale pretty massively, like we are seeing in traditional deep learning with GPT models, as soon as we figure out how to actually do it. And there are data science issues still, but I'm positive that they will be resolved, and then we need the systems issues to be resolved as well.
Yeah, definitely.
Yeah, thank you very much, and hopefully see you in real life at some point.
See you. Bye-bye.
Bye.